Well, let's take the register machine now and actually step through in real detail, so you see completely concrete how some expressions are evaluated. All right, so let's start with a very simple expression. Let's evaluate the expression 1. And we need an environment. So let's imagine that somewhere there's an environment. We'll call it E0. And just, since we'll use these later, we obviously don't really need anything to evaluate 1. But just for reference later, let's assume that E0 has in it an x that's bound to 3 and a y that's bound to 4. Okay? And now what we're going to do is we're going to evaluate 1 in this environment. And so the end register has a pointer to this environment E0. All right, so let's watch that thing go. What I'm going to do is step through the code. And let's see, I'll be the controller. And now what I need, since this gets rather complicated, is a very, very literal execution unit. So here's the execution unit. Okay. 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 All right, now we're going to start. We're going to start the machine at eval dispatch. Right? That's the beginning of this. Eval dispatch is going to look at the expression and dispatch, just like eval. But we look at the very first thing. We branch on whether or not this expression is self-evaluating. Self-evaluating is some abstraction we put into the machine. It's going to be true for numbers to a place called ev self-eval. Right, so me being the controller looks at ev self-eval. So we'll go over to there. ev self-eval says, fine. Assign to val whatever's in the expression unit. Okay. And I have a bug. Because what I didn't do when I initialized this machine is also say what's supposed to happen when it's done. So I should have started out the machine with done being in the continue register. Okay? So we assign to val, and now we go to fetch of continue. And now the machine's... Okay. Okay, let's try something harder. Let's reset the machine here. And we'll put in the expression register x. Okay. Start again at eval dispatch. Check. Is it self-evaluating? No. Is it a variable? Yes. We go off to ev variable. It says assign to val, look up the variable value in the expression register. Okay. Go to fetch of continue.
Done.
Okay. All right, well, that's the basic idea. That's a simple operation of the machine. Now let's actually do something a little bit more interesting. Let's look at the expression. The sum of x and y. Okay, and now we'll see how you start unrolling these expression trees. Okay. Well, start again at eval dispatch. Okay. Self-evaluating, no. Variable, no. All the other special forms which I didn't write down, like quote and lambda and set and whatever, it's none of those. Turns out to be an application. So we go off to ev application. Okay? ev application, remember what it's going to do overall. It is going to evaluate the operator, it's going to evaluate the arguments, and then it's going to go apply them. So before we start, since we're being very literal, we better remember that somewhere in this environment, it's linked to another environment in which plus is bound to the primitive procedure plus before we get an unbound variable here in our machine. Okay, so we're at EV application. Okay, assign to unev the operands of what's in the expression register. Okay, those are the operands. Unev's a temporary register where we're going to save them.
Pipelining.
Okay? Assign to exp the operator. Now notice we've destroyed that expression in exp. But the piece that we need is now in unev. Okay. Now we're going to get set up to recursively evaluate the operator. Save the continue register on the stack. Save the environment. Save unev. Okay, assign to continue a label called eval args. Now what have we done? We've set up for a recursive call. We're about to go to eval dispatch. We've set up for a recursive call to eval dispatch. What did we do? We took the things we're going to need later, those operands that were in unev, the environment in which we're going to eventually have to maybe evaluate those operands, the place we eventually want to go to, which in this case was done. We saved them on the stack. The reason we save them on the stack is because eval dispatch makes no promises about what registers it may destroy. So all that stuff is saved on the stack. Now we've set up eval dispatch's contract. There's a new expression, which is the operator plus, a new environment, although in this case it's the same one, and a new place to go to when you're done, which is eval args. So that's set up. Now we're going to go off to eval dispatch. Here we are back at eval dispatch. It's not self-evaluating. Oh, it's a variable. So we better go off to EV variable. All right? EV variable is assign to val, look up the variable value of the expression. Okay, so val's the primitive procedure plus. Okay, and go to fetch of continue.
Eval args.
Right, which is now eval args, not done. So we come back here at eval args, and what do? We're going to restore the stuff that we saved. So we restore unev. And notice there it wasn't necessary, although in general it would be. It might be some arbitrary evaluation that happened. We restore env. Okay, we assign to fun fetch of val. Okay. Now we're going to go off and start evaluating some arguments. Well, first thing we better do is save fun, because some arbitrary stuff might happen in that evaluation. Okay. We initialize the argument list, assign to argle an empty argument list, and go to eval arg loop. Okay, eval arg loop, the idea of this is we're going to evaluate the pieces of the expressions that are in unev one by one and move them from unevaluated in unev to evaluated in the arg list. Okay, so we save argle because we assign to exp the first operand of the stuff in unev. Now we check and see if that was the last operand. In this case, it is not. All right, so we save the environment. We save unev, because those are all things we might need later. We're going to need the environment to do some more evaluations. We're going to need unev to look at what the rest of those arguments were. We're going to assign continue a place called accumulate args, or accumulate arg. Okay, now we've set up for another call to eval dispatch. Okay? All right, now let me short circuit this so we don't go through the details of eval dispatch. Eval dispatch's contract says I'm going to end up, the world will end up with the value of evaluating this expression in this environment in the val register, and I'll end up there. So we short circuit all of this, and a 3 ends up in val. And when we return from a val dispatch, we're going to return to accumulate arg.
Accumulate arg.
With 3 in the val register. Okay? So that short-circuited that evaluation. Now what do? We're going to go back and look at the rest of the arguments. So we restore unev. We restore env. We restore argle.
One thing. Whoops, parity error. Restore argle.
Okay. Okay, we assign to argle consing on fetch of the value register to what's in argle. Okay, we assign to unev the rest of the operands in fetch of unev. And we go back to a val arg loop.
Val arg loop.
Okay. Now we're about to do the next argument. So the first thing we do is save argle. Okay, we assign to exp the first operand of fetch of unev. Okay, we test and see if that's the last operand. In this case, it is. So we're going to go to a special place that says evaluate the last argument. Because notice, after evaluating the argument, we don't need the environment anymore. That's going to be the difference. So here at eval last arg, which has assigned to continue accumulate last arg. Now we're set up again for eval dispatch. We've got a place to go to when we're done. We've got an expression. We've got an environment. Okay, so we'll short circuit the call to eval dispatch, and what will happen is there's a y there. It's 4 in that environment, so val will end up with 4 in it, and then we're going to end up at accumulate last arg. Okay, so at accumulate last arg, we restore argle. We assign to argle const of fetch of the new value onto it. So we const a 4 onto that. We restore what was saved in the function register. And notice in this case it had not been destroyed, but in general it will be. And now we're ready to go off to applied dispatch. Right, so we've just gone through the eval. We evaluated the argument, the operator, and the arguments, and now we're about to apply them. So we come off to apply dispatch here. Okay. Come off to apply dispatch, and we're going to check whether it's a primitive or compound procedure.
Yes.
Right? So in this case, it's a primitive procedure, and we go off to primitive apply. So we go off to primitive apply, and it says assign to val the result of applying primitive procedure of the function to the argument list.
I don't know how to add. I'm just an execution unit.
Well, I don't know how to add either. I'm just the evaluator. So we need a primitive operator. Let's see. The primitive operator, what's the sum of 3 and 4?
7.
Okay, 7.
Thank you.
Now we restore continue. And we go to fetch of continue.
Done.
Okay. Well, that was in as much detail as you will ever see. We'll never do it in as much detail again. One very important thing to notice is that we just executed a recursive procedure. Right? This whole thing, we used the stack, and the evaluator was recursive. A lot of people think the reason that you need a stack and recursion in an evaluator is because you might be evaluating recursive procedures like factorial or Fibonacci. It's not true. See, notice we did recursion here, and all we evaluated was plus xy. Right? The reason that you need recursion in the evaluator is because the evaluation process itself is recursive. Right? It's not because the procedure that you might be evaluating in Lisp is a recursive procedure. So that's an important thing that people get confused about a lot. The other thing to notice is that when we're done here, right, we're really done. Not only are we at done, but there's no accumulated stuff on the stack. Right? The machine is back to its initial state. Right? So that's part of what it means to be done. Another way to say that is the evaluation process has reduced the expression plus xy to the value here, 7. And by reduced, I mean a very particular thing. It means that there's nothing left on the stack. The machine is now in the same state, except there's something in the value register. It's not part of a subproblem of anything. There's nothing to go back to. Okay, let's break. Question?
The recursion here is in the stack is because the data may be recursive. You may have embedded expressions, for instance.
Yes, because you might have embedded expressions. But again, don't confuse that with what people sometimes mean by the data may be recursive, which is to say you have these sort of list-structured, right, recursive data list operations. That has nothing to do with it. It's simply that the expressions contain sub-expressions. Yeah.
Why is it that the order of the arguments in the arg list got reversed?
Yes, I should have mentioned that. Here, the reason the order is reversed, it's a question of what you mean by reversed. There's I believe it was Newton. The very early part of optics, people realized that when you looked through the lens of your eye, the image was upside down, and there was a lot of argument about why that didn't mean you saw things upside down. So it's sort of the same issue. Reversed from what? See, we just need some convention. So the reason that they're coming out 4-3 is because we're taking unev and constantly the result onto argle. So you have to realize you've made that convention. The place that you have to realize that, well, is actually two places. One is an apply primitive operator, which has to realize that the arguments to primitives go in the opposite order from the way you're writing them down. And the other one is, we'll see later, when you actually go to bind a function's parameters, you should realize the arguments are going to come in from the opposite order of the variables to which you're binding them. So if you just keep track of that, there's no problem. Also, this is completely arbitrary, because if we'd done, say, an iteration through a vector assigning them, they might come out in the other order. Okay, so it's just the convention of the way this particular evaluator works. All right, let's take a break.